All right, let's talk about Euler's method. And Euler's method is another method that we can use to get a sense of the solution of a differential equation. And I've written out a pretty simple differential equation. In fact, this equation can actually be solved fairly quickly analytically, and we'll do that actually in just a little bit. But this is something that we can solve just by integrating and separating the variables and integrating, but not all differential equations are. And what Euler's method does is it gives us a means for still solving some of the more difficult differential equations. Even if we can't analytically exactly find the solution, we could still get a pretty good sense of what its solution should look like as a function. Now, Euler's method is essentially a process by which we're going to use the starting point of a function. And what we're going to do is we're going to effectively stitch together a bunch of tangent lines. Now, why are we able to do that? Well, if you think about it, if when we talked about local linearity or local linearization, we said if this is a curve and this is the point over which we have our point of tangency and our tangent line. We saw that if we were to zoom in really, really close to that point of tangency, let's say I were, for example, just kind of zoning in here on this region here, we would say that that tangent line and that curve are pretty close in behavior, right? That is to say, we could use our tangent line to give us a good sense of how our function is behaving. And if we could then stitch together another tangent line after that point, so let's say starting from here, we were able to stitch together another tangent line, and then from another tangent line, by kind of stitching together a number of small tangent lines from the previous starting point, or kind of starting from the last point, we can actually get a pretty good sense of what our function actually will look like. So just think of it conceptually as just using the tangent line as a way of determining what our function is going to look like or behave near or around a specific point, and then we're going to stitch together another tangent line from that next point. Okay, so if that's a little bit difficult to kind of process right now, let's actually do an example here with this very basic differential equation. So when we're doing Euler's method, it's often a good idea to set up a table for this, and we're going to sketch everything in just a moment. But let's go ahead and let's take a look at this graph. Let's go ahead and set up a table. We're going to need our x value. Okay, we're also going to need our y value, and we're going to need a column to represent our dy dx. And sometimes when people do Euler's method, they often also have a fourth column, which I'll write this as kind of being somewhat optional, if you will, for delta y, or the change in y. Okay, and so our table is going to look like this. Now, in order for us to do Euler's method, we have to establish a couple of um, key features of our method here. First thing, we need to establish a step size. So let me write that out. We need to establish a step size. That is to say, how far apart is our x value is going to be. What is the width between each tangent line, if you will? So let's start with a very basic number to compute kind of without a calculator. Let's just say delta x is equal to 1. Okay, and what we also need is we need an initial condition. Effectively, where are we going to start graphing from? And let's go ahead and start with the point 0, 1 as a starting point. So this is our initial condition or our starting point. So that is to say, we're going to start off from 0, 1. So again, conceptually, the idea here is we're going to try to figure out what the tangent line is at that point and start to stitch together a bunch of tangent lines. Okay, so let's start it. So at our initial condition being 0, 1, our x value is 1, and our y value, or 0, excuse me, and our y value is 1. According to our differential equation, dy dx, what's really nice about this particular differential equation is that it's really easy. It says that the change in y with respect to x is simply going to be whatever your y is. So our dy dx, we look at whatever our y value was, and it's going to be equal to 1. Okay. Now, what about for this delta y thing? What is our change in y going to be? Well, our change in y is going to be whatever our dy dx is times our delta x. And another way of thinking about delta x is dx. All it is, it's the change in x, right? It's the change in x. Okay, and we see here that our delta y is just whatever our change in y is. So what we're going to do is we're going to multiply together our dy dx times what our delta x was, or dx. So our change in y, we said dy dx is going to be our previous value, 1, times our delta x, which is 1. So our change in y is 1. So how do we use that? Well, our next x value is going to be at 1 because we said our delta x was equal to 1. So we're going to be 1 unit apart. And then our new y value here is whatever our previous y value was, which was 1, plus our change in y, which was 1. So this is 1 plus 1, and this is going to give us 2. Now, what is our new dy dx? This is going to be equal to 2 because it's whatever our y value is. Now, what is our delta y? It's our previous dy dx times delta x. So it's 2 times 1, which is what gives us 2. Now, at our next step, x is equal to 2, right? Because again, our delta x is 1. Our new y value is whatever our previous y value was, plus our change in y, which is equal to 4. And our dy dx is now 4. So I'm going to pause for a second. I'm not done with this method, but I kind of also want to just sketch together what I'm doing so far so you can hopefully make a little bit more sense of this. We said our initial condition was 0, 1, okay? And we can think of 0, 1. At this point here, I'm going to kind of stitch together a tangent line with a slope of 1, right? A tangent line with a slope of 1. And I'm going to stop once I get to my delta x, which was equal to 1, right? Now, this is my new point. Now, what is this coordinate? It's the coordinate 1, 2, which is what I see here. X is 1, y is 2. Now, from here, I'm going to sketch another tangent line. This time, what is the slope of my new tangent line? It is what's given by dy dx. So I'm now going to sketch a tangent line with a slope, a rise of 2 over 1. So here's my tangent line here, okay, with a slope of 2. So hopefully you can kind of see that as well, all right? And I stop because my delta x is 1, so I'm now here at this point, okay? Now at this point, at the point 2, 4, which was this coordinate here at 2, 4, what is my dy dx now? My slope is 4 over 1. So I'm going to go up 4 with a run of 1. So now here's that tangent line, okay? And hopefully you're seeing what we're doing right now. We're stitching together all of these tangent lines from the previous point. What is our change in y now? Our change in y is dy dx, which was 4, times our step in 1. So this conceptually makes a lot of sense. We're basically saying now, at this point, at our previous point, we're now going to stitch together a change in a vertical change of 4. So now, for my previous step, this was 4. So if I had to graph another point, I would say our new y value would then be 8. And what do you know? That does seem to match up with the point 3, 8, which is right here. Okay, and I could keep on doing this, and that's another thing that will probably need to be stated at the beginning of the problem. Right now, we're treating this n here. This is n is equal to 0. So let's just stop here until we get to n is equal to 3, and we could keep on doing this. Now, let's go ahead and let's compare what we've just graphed here, all right, and with what the actual solution might be. All right, so we kind of have a sense of how the function is behaving. Now, how can we determine this analytically? Well, let's go ahead and let's do that. So our original equations, let me just kind of show this here. Our original equation was dy dx is equal to y. We're going to separate our variables, which gives us 1 over y dy, which is equal to dx. We're now going to integrate both sides. We're going to integrate the left side with respect to y, which is going to give us the natural log of the absolute value of y. And this right side here is going to be x plus some constant. And I'll call this c sub 1 because I may need to change that. We're now going to exponentiate both sides. That is to write each of these sides as the power of our exponent. And e raised to the natural log of some argument is just that argument itself, so the absolute value of y. Now, this here, I'm going to let c, big C here, be equal to plus or minus e to the c sub 1. And I discussed this in a previous video of how we're able to do this, but effectively we're just using exponent properties, right? We're rewriting e to the x plus c sub 1. I apologize, I actually had it right the first time. Plus c sub 1 as e to the x times e to the c sub 1, right? So we then have big C is our plus or minus e to the c sub 1, right? And that's going to take care of our absolute value, e to the x. And if we now plug in our initial condition, let me just get this out of the way. If we now plug in our initial condition, which we said was 0, 1, I can now solve for c. Y is 1, e to the 0 is 1, so c is equal to 1. So y is equal to just e to the x. This is our particular solution that goes to the point 0, 1. Now let's compare that with what we have up here. So if we know that our function, our solution is supposed to be e to the x, let's graph that. Well, we know that when x is equal to 0, y is equal to 1. And we also know that when x is equal to 1, y is approximately 2.718, which is right around here. And when x is equal to 2, y is equal to a little less than 7. So it actually gives us a curve. Let me actually do this. That looks something like this. This is not a great curve, but that's mainly because I scaled my axes pretty terribly. But you can kind of get a sense of what this should look like. Okay, this is my curve here. So how close was I? Well, it was okay. It was an okay approximation. Now, ask yourself, how could I have gotten a better approximation out of using Euler's method? And the answer is having used a smaller step size. Our step size was 1, which means our tangent lines are going to be pretty large. But if I had been able to stitch together, let me just do this in a different color, a bunch of smaller tangent lines, right? We might have been able to get a much better approximation of how the function is actually behaving. And that's actually what I'm going to have you do next. So I want you to repeat this problem now, but I want you to do this time with a step size of being 0.1. You can check your solutions with what I have in Schoology, but hopefully this video helps give you a pretty good sense of how Euler's method works in helping us with differential equation solutions.